Talk. Can everybody please get seated? Okay, so this talk is about the state of the art in decrypting the GSM encryption, which is called A5. Some of you may have heard a similar talk on a past conference by other people who said basically the same things. We have the means and we know how to do it. And that said things like, yeah, probably in May 2008, we will have a table, a rainbow table, to release so that everybody can decrypt GSM, but somehow this table never got released. That was the previous project run by THC, and that kind of petered out. So there were basically clear signs of interference from the government that may or may not have caused the non-releasing of the table. The fact is, THC tried to centralize the approach, basically calculating the table on a cluster of FPGAs and promising to release them, and which created a single point of failure, and that single point of failure failed. The table never got released. So this is basically the next try of getting GSM decryption into public hands to know how it works, to show how insecure it is. And this is what Carsten is going to talk about now.
Yeah, good afternoon. Good to be here again. It's my pleasure to bring back this topic once again to a hacker conference and have once again the promise upstanding that in a few months from now we will be able to decrypt GSM traffic. As Frank was pointing out, there won't be a single point of failure this time, especially it won't be me. I'm going to give you all today's software, and I'm going to ask all of you to use that software to generate some tables that in a few months from now will enable us to decrypt cell phone, voice, and data. Okay, let's get going at that. A5 the cipher within GSM, has been broken over and over and over again in the academic domain. It has been shown to be statistically weak. It has been shown to be vulnerable to certain pre-computation attacks. It has been shown to be vulnerable to attacks where you only need short amount of known data, which is exactly where all these attacks break. Usually you don't have any amount of known data. So while this cipher has been broken over and over and over again, it hasn't actually ever been publicly broken. We know, however, that it is entirely possible. There's commercial solution available only to the intelligence community, from what I understand, that will break A51 for you. And of course, there's the much talked about GSM cracking project that did have a roadmap of releasing tables to the public that broke at the very last minute. So we know, however, that there is a way of breaking A51. And we just took these bits and pieces and moved them in a more distributed, towards a more distributed approach, which is what I'm going to share with you today. First off, though, GSM is a very, very widely distributed technology. I would say the most widely distributed mobile technology existing so far. So a good chunk of the population of Earth is using this right now, which I was surprised by. At least Wikipedia is claiming this number. What we do know, though, is that when we go around the world with our GSM phones, they work pretty much in every country other than in Eastern Asia. So we're looking at a technology that a lot of people rely on for mostly privacy, but also data security in the form of authentication code sent through text message. GSM, for that very reason, always had security built into it. Even before the standard was first implemented, there was already a suite of encryption ciphers, and most countries chose to implement a reasonably secure cipher from their point of view. Now, this is a long time ago, and nobody would expect an industrial cipher to last this long. It has been keeping up pretty well, but statistical attacks were always possible. The first ones, shortly after this cipher was released into the public domain in '94. Now it's 15 years later, and we still don't have a proof of this actually being a problem. And due to that fact, more and more applications that are security sensitive adopt GSM technology as a security base. I was shocked to see that my current client is moving from RSA secure ID, hash chain tokens, to sending people text messages whenever they want to log into their secure email account. So people are moving away from reasonably secure, almost provably secure technology to a cipher that has been shown insecure 15 years ago. Other financial transaction applications adapting this in banking as well as payment, and so do access control applications. So this is a spreading security technology that everybody seems to be relying on because it was never publicly broken, right? As I was saying earlier, all the academic hacks rely on the fact that you know some part of known plain text, as they call it, meaning if you knew the first 2 seconds of a conversation, you could decode the rest of it. Now, when do you ever have the situation that you can record some of a conversation but not the rest, and record it in a way that would allow you to compute the compressed, condensed version that's going over the air? So this is an assumption that in reality never holds true, and especially doesn't hold true in text messages where there isn't enough plain text to begin with. So all of these academic hacks, as beautiful as they are mathematically, do not apply to GSM, but rather apply to the A5 cipher used within GSM, but not the way it is being used. Further along the road, as computational resources become cheaper and cheaper, it was shown that you could exhaustively try all possible keys for A5 with sufficient computational resources. Of course, if the incentives are high enough, this is actually a worry, but since we want to show this in kind of a do-it-yourself environment, that it's not even secure enough for micropayment, this attack might not be of concern. It's certainly still expensive. You need something like $100,000 cluster to break it within a day. So you can decode 1 text message per day with that machine. Then last year we were promised the rainbow tables, which from our point of view seems the best possible approach, even though it doesn't even exploit any weakness of A5 other than its small key size. And we still think this approach is viable, and we implemented tools to compute these rainbow tables, again, trying not to be intimidated in the same way that the original authors of this idea were. The process, as I imagine it going forward now, and most of this has been done already, find an as cheap as possible, as fast as possible engine that can crunch through A5 as efficiently as possible. Then use this engine in a distributed fashion to compute tables. First, of course, set up the way of distributing it and the table parameters. And finally, bring together all these tables to whoever wants to show this to be insecure, or preferably even keep them distributed and only collaboratively ever break packets. So to keep it a public proof of concept rather than a one-person exploit tool. Now, as I was saying, most of this is already done. We did implement a number cruncher on graphics cards, and we did compute the best possible way of using known rainbow table and distinguished point techniques to generate tables from those. And I would like to ask a couple of you at least to download this right now, so we have at least a few mirrors. I don't know when I'll get the first email to take this down, but I want this to be spreading as soon as possible. And now here's where you get involved. We need computational resources to compute these tables. We don't want to do it in any central location, and preferably we don't want anybody to ever have all the tables, but of course that's up to you. We need specifically CUDA graphics cards, that is NVIDIA graphics cards, or we need FPGAs. That's a more specialized type of hardware, much more efficient though still. Now, quick poll, how many gamers are in the room with a good NVIDIA graphics adapter? Yeah, okay. That could almost do it already. We need a couple of dozen, preferably around 80 if we want to be done by the end of the year. So that's a good start. Go ahead, download the software. I'll, for the rest of the next half an hour or so, be talking about how we've been optimizing this engine and how we have been computing these table parameters. The basic message, though, is on this slide. Go ahead and help us compute the tables. Now, a little bit of cryptographic background. What technique are we using to break this cipher? We're using, as I was saying, a technique that doesn't even exploit the statistical weaknesses of the cipher, but rather a generic technique. That's why this might be interesting for you too if you want to break other ciphers with small key sizes. 64 bits seems around the limit that you can be pushing. So we are looking at a codebook computation attack, where a codebook is a mapping from all the outputs back to the secret information that went in the first place to compute these outputs. So in the case of a stream cipher, that is the secret state. If you know the secret state, you can compute the key stream that comes out of it that is used to encrypt an entire voice call or a text message. So we want a mapping from the output that we see going over the air back to the secret information that went in generating this. And now imagine you had a book, like a phone book, where it's ordered by the output and it points out to you the secret state that was in it. All you need to do once you see something flowing over the air is look up that information and you get the secret state. Easy enough, right? Codebook attack. Now there's two limitations we need to overcome to make this practical. First of all, this codebook, even though A51 uses a small key, is still 128 petabytes, which might be more than storage available on Earth. At least more than we'll ever get together for this project. So we need one way of compressing this codebook to store it more efficiently. Another limitation is if we just went ahead and computed this with Intel processors, it would take us a combined 100,000 years, probably much more even, depending on the optimizations we can do. So we also need to make it faster. Even among all of us, we don't want to spend 100,000 computing years on this. And that's the two optimizations I'll be briefly talking about that make this practical. So to make the computation much faster, we did a couple of things that differ for the platform this is being computed on. For the CUDA card, we maximize the number of parallel instances we can run on this existing processor. Unlike an Intel processor, where now you have something like 2 cores, maybe 4 in server processors, a CUDA gives you a couple of 100 cores, each of which can be used to crunch its own A5 computation. So right there you get 100 times or more speed up. On FPGAs, you can parallelize even more. You're very flexible. In FPGAs, you're not talking about the number of cores, but rather what resources you can just puzzle together to form whatever you want. And if it's small enough, you can use many parallel instances, thousands in fact, on a good Vertex FPGA these days. So that gives us a couple hundred to 1,000 times speed up. Then the next optimization, the next layer of the optimization we did is on the CUDA graphics card, try to utilize the available resources, especially SRAM in this case, as much as possible to parallelize the computation as is. So to jump ahead a couple of computation steps, in this case, we had a 4 times speed improvement through that alone. So instead of 240, we only need 80 CUDA cards now. On an FPGA, the optimizations are a little different since the clocking rate is variable. You get more speed from simplicity. It's a beautiful design goal to have it as simple as possible, to be as fast as possible. We don't really have that in software anymore much. So that's the different layers of optimization. And we reach a very achievable goal of spending 3 computational months on 80 computing nodes. Any of your gaming machines will do, or on about 20 mid-range vertex processors. So if anybody has FPGA resources, we'll be more than happy to use those too. Let me just do one deep dive into the technical details. The source code is available, so any questions should be answered through that. But let me do one deep dive into how we did the 4 times speed up on the CUDA card, which might be interesting to you just to see the different trade-offs of the CUDA as compared to either FPGAs or CPUs. So the A5 algorithm has 64 bits in its state, split across 3 different registers. Each of these registers may shift 1 over in every clock, and then the empty slot on the left needs to be filled, of course. Now, a simple implementation of this would compute, based on all the 64 bits, which 3 bits need to be shifted in, and then shift 1 over, move those in. That is slow. Shifts are extremely slow in software, and CUDA is, for the most part, a software-driven system. So if there was any way of computing several such shifts at once, it would speed it up significantly. Now, it turns out that only a subset of the bits in the state of these 64 bits is needed to compute what is coming next. So in this case, only the state bits in the boxes are needed to compute the next 4 shifts, right? So what we do is have lookup tables in the very fast SRAM that basically comes for free. So one clock cycle access to look up those next 4 bits that come in. The exact way this is being looked up is shown here for one example. And so just going through these lookups will give us the next 4 shifts, and we get a 4 times speed up since the shifts are really the bottleneck. That's just as one design optimization, or an example of which, where you now use the free SRAM for speed up. On the FPGA, we do similar tweaks to keep it as simple as possible and maximizing the throughput. Now, are there any questions so far as to the implementation? I know this is kind of, for some of you, very interesting. For others, you're like, oh, let's get to the table computation. We want to get going. But are there any questions, or can we leave that behind us? Okay, so table computation. What I'll be discussing now is several techniques out of the domain of pre-computation attacks, these codebook attacks, right? We already said the simplest possible codebook is not going to fit on any possible hard disk, even though we now have the resources of generating the data. We can't possibly store them. So what we're doing is we're storing them compressed, you could say. And here's how. Instead of only saving storing input values and output values from one computation, we do several computation and only store the first and the last value. So the idea behind this is that if you, in the table that on hard disk is only the left and the right column, but in the computation includes all the values in between, you can look up any value in between without actually storing them. So the function k is always the same. In this case, it's the A5 function. And say you were looking at an output of 2F06, right? From this picture, we know that the secret key that went in is E233, but we don't intuitively know that if we only store the green and the yellow column on the hard disk. So what we're doing is applying the k function, the A5 to it over and over again until we hit a value in the yellow column. So in this case, we would apply it once, look up, is the 503A on hard disk in the yellow column? No, it's not. Do it once more, and we find a value that in fact is on hard disk. We then go back to the green value corresponding to it, and from there find the key that went into computing this, because it's in the same chain, right? Does this make any sense? So if the output you're observing over the air is anywhere in this table, the computed part of the table, not the stored part, you will find its corresponding secret key by doing just a couple of computations and a couple of hard disk lookups. Does that make sense? So, of course, you can store this as small as you want by having these chains be longer. The longer the chain becomes, the smaller the table has to become, because the entirety of it has to cover something like 2 to the 57 values. Now, here's the bottleneck of this system. To make this practical at all, the chain needs lengths somewhere far exceeding millions. So for each lookup now, you have millions of hard disk seeks. Of course, that is your bottleneck now. You have millions of computations at the same time, but those will be much, much faster. So some smart academic came along with an optimization to cut down on the number of hard disk seeks to get away with that bottleneck, at least now in the breaking of the cipher. And the way this is working is called distinguished points, is by only storing values that have a certain pattern. In this case, the pattern is have the last 8 bits be 0. So only store those on hard disk. And while you're computing, don't compute a certain number of chain links, but rather until you hit one such distinguished point, right? So now on the attacking side again, you start with some values, say the F415, and you'll compute without looking at the hard disk until you hit a distinguished point, until you see the 8 0 bits, and only then you look at the hard disk, right? Much more efficient, much better balance between computing and hard disk seeks. This is way more optimal than the simple pre-computation attack, but still not entirely perfect, since you have a big problem with collisions. Collisions are places where if somewhere in the table the same value appears twice. Now from there on out, it will be the same deterministic, apply A5 to it over and over again until you hit the same distinguished point. So if as your table grows, you'll get more and more redundancy in your table, and eventually you won't be able to add any useful information because everything will collide. So you have to move to more tables, you have to compute several tables in parallel, which of course, if you compute n tables, makes it n times slower to find a key. And there's a trade-off. Now let me introduce another optimization to the original technique that gets away with the collision, and then we'll combine the two. And now this is finally what's called rainbow tables. Usually all of this is referred to as rainbow tables, I guess because it's such a beautiful name, but really only this is the rainbow table now. In this case, you prevent collisions by having a different function on each link of the chain. Now, different doesn't need to be completely different. It could all be A51 with a constant, a different constant XORed into it. So they're slightly different, but different enough from a cryptographic standpoint. Now, if in two places of the table the same values appear, they won't lead to a merger and all that redundancy, but rather, since the next link is most likely a different function, will divert again. So that's the rainbows. Unless you're hitting the same color at the same time with the same value, you won't have a merger, right? Much fewer collisions. You can have much larger tables. There is, however, a downside to it, as is always with cryptography. Instead of now computing your applying your function over and over again until you hit a certain criteria and look at the hard disk, you have to go through these chains multiple times. So you start by only applying the last rainbow color, look it up on the hard disk. Then the last two, look it up on the hard disk. Then the last three, and so forth. So as the table becomes wider, it gets exponentially more expensive to find something in the table. So here we have an optimization that, as it's applied more, it eventually goes into a bad trade-off. Now that sounds like something we could perfectly combine with the other optimization that only runs into the problem of collisions, and that's in fact what we did. So for A5.1, we compute a distinguished point rainbow table, where we compute a distinguished point not once but 32 times, and each time we hit a distinguished point, we change the color. So this is drawing in the best features of both worlds, and the number 32, of course, was found through an optimization problem and seems optimal for the 2 to the 57 key space. I'll be happy to share the calculation with you if anybody's interested. Point being, though, we did a lot of calculation to make sure you're not computing too much. This is, from all that's known cryptographically, the best possible pre-computation attack on A5.1. And now let's get back to the main reason why I'm standing here. We still need your computational power. So the process, well, let me first give you a second. Well, I've already given you two reasons, I guess, for distributed. First, it's much faster, but second, nobody is liable for it as in one person. We need this to be done anonymously, at least in parts, and we need this to be distributed, preferably across different jurisdictions. And the process I would propose going forward with this is get the tools, of course, they're online. You can read the documentation on all that, and then start cracking on these tables. There isn't even any coordination needed. We don't need to exchange emails unless somebody doesn't understand the software, say, which might very well be the case. So we might need to go through some code revision or documentation stages. But unless that's the case, you don't need any input from us. Generate two random numbers and start crunching on these tables. Eventually, once you're done, put the tables on BitTorrent, through Tor preferably, so there's no way of tracing the tables back to any one person. Once we hit something like a terabyte of tables, we have a good chance of decrypting a lot of GSM packets. Eventually, the goal is to have something around 3 terabytes by the end of this year. Right? Does that sound doable? I mean, we're a bunch of people. If everybody computed 5 gigabyte on 80 nodes, something like that, we'll be done soon. Okay, well, that's my proposal for the process, but of course, it's your software now. It's GPL, so do with it whatever you want. Any optimization is welcome. We want you to be involved, of course, not just as computational resources, but as developers as well. We did build this framework to be as flexible as possible, both in the number of backends it supports. So I've been talking about CUDA and FPGAs. CPUs are supported, of course, as well. And it's flexible for more possible backends. It is flexible as in the cryptographic function to be used as well. So if you have any other cipher with 64-bit or less of a key space, you can adopt this very, very quickly to just suit your project pre-computation needs. So please get involved both on the computation side and as developers. Sasha has been spending a lot of time developing this, and it's a beautiful framework. And it would be a pity if this was only used once to compute these tables and not used any further. Well, with that, I think I've made my point clear and perhaps raised some interesting questions as to whether one should subvert the technology that 3 billion people rely on for their privacy. And I would suggest for the remainder of the hour to have Harald and Frank come back on stage, and for the three of us to engage in a discussion with you as to whether this makes sense, and we all want to go ahead showing that this technology is not to be used for any more security applications more than it already is. With that, thank you very much.
So, questions?
So, Carsten, first questions, and apologies in advance. I have to put the devil's advocate hat here on.
Go ahead.
What are your thoughts and considerations on possible poisoning of those computed tables? Because this is something that immediately crossed my mind. How do we ensure quality if we get into this?
Well, yeah, so the question is how do we prevent that somebody uploads bogus data and makes it available anonymously through BitTorrent? Well, that's easily answered. It is statistically very easy to test whether a table contains the right information or not without downloading the entire table. So you would fetch a few random blocks through the BitTorrent, and with just a few computations, you can, with the 99+ probability, test whether this is the data you want. So definitely something we considered in the design of this. But thanks for the question.
Just from my understanding, this rainbow table that we're then calculating, you don't need any coordination to say you start at the keys with 0001, you start at some other point. It's just we all take some part of this cloud, and the more cloud you have, the quicker it is to crack calls.
Yes.
It's just the random cloud that everybody has a part of. It's holographic, if you will.
Right. So there's no coordination needed other than you shouldn't choose the same 32-bit random number. So patch your Debian box before starting. Right?
You seem very worried about the legal aspects of this problem or of this project. Is there a specific reason for this? You mentioned that the previously calculated table never was released.
Right, it was not. Well, to answer the first part of your question, no, I'm not worried, since all I did was put some software on the internet, right? That is crunching numbers.
Okay, regarding the legal aspects, building this tool is certainly not illegal. Using it for intercepting other people's phone calls would be illegal, which we will not do. This is a proof of concept, so we're trying to show that it's doable. That is the goal of the exercise. Regarding why has this been set up so paranoid again in a distributed way with no single point of failure and so on. The reason is that the statistics that the attack has been out for so long, the knowledge about the possibility of the attack versus the availability of this attack in a practical domain seems to point that there are interests out there that want to prevent this to get into the public hands. And if you look at who is buying these systems today, it's mostly intelligence agencies, so they know that it works and they know that it can be done. But they also know that the people that tell them what to do, namely politicians and big business bosses, they don't use encryption at all. They use GSM phones like we do, which means that as soon as somebody really builds a GSM interceptor for the masses, they are into all kinds of problems. And so there is a certain pressure from governments to prevent this. So this is why this project has been set up in a way that it's as distributed as possible and as not mean-acing as possible.
Any more opinions on that?
Nothing bad except for a few problems at the border, but somehow they are convinced to not do this anymore. So, I have no clue. So they just say they don't want to work in this domain publicly anymore. So there are endless amounts of rumors which I will not repeat here, but it boils down to the table has not been released, the project has been dead before we basically reanimated it.
Hi, you mentioned it's possible to check the validity of a BitTorrent before downloading the whole thing. Does such a tool exist, or does that need to still be written? And secondly, is there any particular place that you'd recommend advertising the .torrent files?
Well, the way I understand BitTorrent is that you randomly seek the file anyhow. So whatever part of the file you download first, just run some checks on that. I don't think there's more software needed on the BitTorrent side. Yes, we do have the tools that would check whether any part of the table is consistent. Right?
Is that on the track as well, yeah?
Yes.
Okay. And for advertising the .torrent files, once you've made the torrent and uploaded it and stuff?
Well, we have a Tor expert here. I believe there is a BitTorrent tracker within the Tor cloud somewhere. Is that so, Jake?
Okay, so Tor and BitTorrent is a touchy subject because Tor is breaking because under the load of BitTorrent. So please don't transmit the files over Tor, but only get the tracker data over Tor.
Sounds good. Thanks.
So any volunteers for FPGA clusters?
Yes. Yeah.
Question
Well,
was,
if one person had all the resources in one place, could it be parallelized to just run it on, say, 32 FPGAs at once? And yes, of course. You need some power to go in there. It will cost you, yeah, but we'll catch up later. Any more questions? Any more opinions? As in,
please use the microphone.
don't break the security base of my bank, please. Can we have somebody say that?
Wrong audience for that.
Well, but
that would be worthwhile.
a ridiculous point of view. The next bank is going to adopt it if we don't do this, right? No, well, I appreciate that you're an audience that doesn't bring up this point because we all understand that, of course, full disclosure, 15 years into vulnerability is most urgently needed. Thanks. Sorry, I didn't mean to cut you guys off.
Oh,
Go
no
ahead.
problem. So, I mean, basically, there are other vulnerabilities that are 35 years old, like DNS. So there are cool things that now DNSSEC will allow us to do. For instance, encrypted voice calls over SIP, over data networks. So I'm very happy for you guys to do this because there will be solutions in time for people that want valid and encrypted things once this table is done. So.
Yes, well,
and that'll be that means that people can have encryption. People should have encryption.
Yeah, essentially, this series of talks is to provide you ample warning, so everybody can already think about what to do then.
If people plan to build such software, come over to the booth there. We're happy to fund you. We're a funding agency, so.
Thanks. Good offer.
Hi, I just had a look at the subversion code of the FPGA, and it looks like it's a Milky Mist SoC. It's a micro 32 CPU in there, but I didn't see the actual FPGA code of the thing that computes these numbers. Do you know if the FPGA code in the subversion is usable, or is it just a demo thing?
Let's get together here afterwards with the FPGA developer. He's somewhere. I've seen him earlier. We'll figure things out. Everything should be in the subversion, but we've really been concentrating on the CUDA part so far.
Once there's a discrepancy between the 3 months we need to get these tables, say Congress, and the 1 to 2 years that Harald was mentioning in when people will be running around having clear text on their drives. Where does the other 1 year and 9 months go? What's still needed in the meantime?
Well, I think it's, on the one hand, it's probably a different level of optimism versus pessimism. Many people have accused me of being overly pessimistic with things. So,
80 people, come on, don't let me down, guys. 80 people.
Yeah, so, well, as I indicated, there are many parts of the receiver software that need to be done. So far, we only have the downlink. There is no uplink receiver code. The user interface is non-existent. The quality of the received signal is not high enough, and so on. So there's many areas that need work on the actual GSM receiver side inside AirPro. And it's a question of how many people will contribute to that. It's not that, the people who are working on AirProbe now are, the providers of something and everyone else is consuming it. We are a community, and there is the point in time upon which a certain project will be finished depends on how much contribution the project gets, like any other open source project as well. So, he needs people for, helping him to compute, but he already had other people who helped him on, with the actual implementations that are there now. And maybe in a month or in 2 weeks or whatever, some super brilliant CUDA or FPGA hacker has optimized the code even further. And just like our receiver software right now, it's like, it's barely able to do a halfway decent job, but maybe in 2 or 3 weeks somebody has solved the problem because he has the expertise in that particular area. I'm not a digital signal processing guy. Other people are.
Hi, I wondered, Harald, if you're planning to implement A5 and OpenBSC so that we can run our own test networks and then crack them? Because I think that would make it a lot, like I have the BS11 and I have the GNU radio, and if I could do the whole thing all at once, it would work well with the FPGAs.
Yeah, so the question, if I understood correctly, was when will there be encryption in OpenBSC? Support for encryption. Well, once again, is as soon as somebody implements it, as always. It's not hard. There's already one of our developers, Dieter, he already had a proof of concept implementation and it worked. All that the BSC or the higher levels of the network management need to do is to tell the BTS the correct key and tell it switch on encryption. That's it. Yes. Well, of course, if you want to have encryption, you need to know the KI, the internal key of the SIM card. But like if you have at home, you have a BS11 or some other BTS, and you have a couple of phones, and you buy some, readily available cheap Chinese cloning SIM cards where you can manually set the key. Then you can set the key, thereby knowing the key inside the SIM card, and then you can trigger the authentication algorithm, and you can set the resulting session key into the BTS. But the OpenBSC or any other BSC software does not need to know the algorithm or not do any cryptographic computation by itself.
Is there a need for someone to, I have one of those, I was in China, I have one of those programmable SIM cards. Is there a need for someone to write some software to program SIM cards, or has that already been done?
Well, so far I do not know any free software, open source software that ships or that can be used on these SIM cards. All the vendors ship is you get the SIM card and you get some Windows proprietary software for setting the actual key. I haven't looked at the protocol yet that they talk, so yes, there is a need for a free software program that can write to those to these writable SIM cards.
Cool.
Any more questions?
Okay, then thanks for attending and happy computing.